Pre-calculus section 4.8 on using trig and applications. First example, we have this isosceles triangle. The legs are 10, the angle between them is 18 degrees. If we draw in this altitude, that altitude is also going to bisect that angle at the top. So now in this green triangle, we know the angles are now 9 degrees and 9 degrees on the other side. Cosine of 9 degrees equals x over 10, and then when we solve that equation for x, we get about 9.88 meters. Here's our next example. We've got the airplane and we've got our home. In the initial scenario, we have this yellow triangle. The angle of elevation is 8 degrees. We don't know how far away the plane is. We don't know its elevation. In the second scenario, 2 minutes later, we have this triangle, and the angle of elevation is 13 degrees. The elevation itself is still x, and the distance is now y. But since the airplane is traveling 750 miles per hour, we can do speed times time to figure out the distance. Here is our speed in miles per hour. 2 minutes is 2/60ths of an hour, so if we multiply those, we can see that the airplane has traveled 25 miles in those 2 minutes. So then, based on these two different scenarios, we're going to get two different equations. So we have this triangle, which would tell us that the tangent of 13 is equal to x over y. And we also have this yellow triangle, the original one, and in that the tangent of 8 degrees is equal to x over y plus 25. Two equations, the same two variables, so we have to use some good algebra skills here. And the first one I solved it for x. The second one I solved for x. And then really by a transitive or kind of a substitution, we set y tangent of 13 equal to this equation from the left side. And we do some algebra to solve that, move all of our y's to the same side. The numbers to the other side, we get y is about 38.90 miles. And since we know that x equals y times the tangent of 13, we can plug that in for y and get that x is about 8.98 miles up in the air. This is problem number 3. We have the line of the kite is 100 feet. The angle of elevation is 50 degrees. So then the height of the kite can be found by taking the tangent of 50, or excuse me, the sine of 50 degrees equals x over 100. Solve that for x, we get about 76.6 feet. Problem number 4, we don't normally see this terminology in our math problems, but it's what you would see if you're actually out in the mountain. It says a road sign at the top of a mountain indicates that for the next 4 miles, the grade is 12%. So that means x over y is 12% or 0.12. In terms of trig, we would say that the tangent of theta is equal to this x over y. So that means the tangent of theta must be equal to 0.12. Tangent of theta is x over y. We said that was 0.12. So the tangent of theta is this. Take the tangent inverse and we see that the angle itself is about 6.8 degrees. That's the angle of the grade. The change in elevation is how much did you actually go up. That's the x value. Now since we know that theta is about 6.8 degrees, use that exact value in your calculator and we can figure out that x is about 0.48 miles. Problem number 5, we have the airplane flying at an altitude of 25,000 feet. Sees the two towns to the right. The angles of depression to the towns are 30 degrees for the one that's farther away and 48 degrees for the one that's closer. The tangent of 48 degrees is equal to opposite over adjacent. So using that, we can solve for x, then store that value in the calculator. It's about 22,510. And then in this other triangle, the tangent of 30 is opposite over adjacent. That would be x plus y for the adjacent. X is a value, it's stored in the calculator, so it's not a number, or excuse me, it is a number, it's not a variable. Multiply both sides by this to get it out of the denominator. And the goal here is to solve for y because that's the distance between the two cities. So move this x tan 30 to the other side. Divide both sides by the tangent of 30. Now y is all by itself. Evaluate the numerator, divided by the denominator, and we get about 20,791 feet. And generally, when we talk about cities, we talk about the distance in miles. So if you divided this by 5,260 feet, we get 3.94 miles. Bearings. We read bearings, middle, end, beginning. So 46 degrees east of south. In other words, it's not going directly south. We have to rotate 46 degrees to the east of south. And so then this is what our bearing looks like, and our 46 degrees is right there. Unlike angles on a graph where we always measure relative to the x-axis, these are always measured relative to the north-south axis. So it's not, this one is not going north, it's going 17 degrees west of north. And this one is going 80 degrees to the east. of north. It's not going north, rotate 80 degrees of the north. Problem number 10, here is our drawing. It's going 29 degrees west of south, so it is going in that direction. 20 knots for 6 hours means it's going to travel 120 nautical miles. So when we're trying to find how many miles west will the ship have traveled by 6 p.m., we're going to say that the sine of 29 degrees is W divided by 120. And you solve that, you get it's 58.2 miles west. We want to figure out the south. The cosine of 29 degrees is S over 120. Solve for that, and we see it's 105.0 miles south of its initial location. So the two components from the beginning, about 58 miles to the west and about 105 miles to the south. In this problem, the Earth is a sphere, has a radius of about 6,400 kilometers. So if two cities have the same longitude, then we can look at their latitude as being a difference of 30 degrees and think of the sphere as being just a circle at this point. And this arc length is the distance between them. We would say that the arc length is r times theta, where theta is measured in radians. So 30 degrees is pi over 6, 6,400 is the radius. Multiply those, and we get that the distance between them is about 3,351.03 kilometers.